All right, ladies and gentlemen, welcome to your notes over sound waves. If you'll just fill this out with me as I talk and go over sound waves and talk about them real quick. So first of all, sound waves are mechanical waves. We talked about mechanical waves in the last note set. So a mechanical wave is a disturbance in space that requires a medium to travel through. So sound does require a medium. There's no sound in space because there's no air in space. There's no medium through which it can travel. What type of waves produce sound, longitudinal or transverse? Well, the answer to that's going to be longitudinal, right? So what I've got here is a little animation. Picture this red line as being a speaker. Okay, so the speaker's bouncing in and out, back and forth it goes. As it does that, when it bounces in, it pushes together all these little air molecules. Okay, those air molecules then hit the air molecules next to them, which hit the air molecules next to them, on and on they go. So what we're getting here is we're getting areas of high compression, right, followed by areas of low compression. High, low, high, low, high, low. And that's our definition of a longitudinal wave. So let's recall the anatomy of a wave. So how do frequency and wavelength affect sound? What about amplitude? Okay, so the speed of a wave should be constant for a given medium. For most sound waves, we're talking about the sound wave traveling through air. As long as that air is at the same temperature and at the same pressure, then the sound wave will travel at a constant speed. So as we increase frequency, the wavelength of the sound wave will get smaller. Okay, as we increase the frequency, the wavelength will get smaller. Well, what about the amplitude, right? So the amplitude is how compressed or how expanded exactly do these get, right? The frequency is how often this is compressing it, right? Back and forth so many times per second. But how much it gets compressed is the amplitude. And as far as sound waves go, that's volume, okay? The more amplitude there is, the more compression there is there, the louder the sound wave will be. So frequency and wavelength both affect the pitch, right? As one goes up, the other goes down, and that's how high or how low pitched a sound wave is. Whereas amplitude is going to affect the volume. Okay, so let's talk about wave interference. So interference is what occurs when two waves meet while traveling. Constructive interference happens when both waves meeting have the same direction of displacement. Destructive interference happens when the waves meeting have opposite directions of displacement. So what does that mean exactly, right? So imagine the red and the blue line are being the two waves that are going to come together and cross, right? So because sound or waves in general, the actual medium itself is not moving. I'm not moving matter, but I'm moving energy. So the energy will actually pass through each other and then keep on going. Let's assume this red wave started way out here and it was a pulse upward. The blue wave starts way over here. That's a pulse upward. When they meet and they overlap, that's when I get this green wave. So because the red was up, the blue was up, we get an even larger wave as a result. Now, I could also have constructive interference where they're both down pulses, right? Let's assume that the red pulse was down and the blue pulse was down. Well, when they overlap, I get this green pulse, which is even larger but still in the down direction. Okay? That's both constructive interference. Over here, I had the example of destructive interference. So this is where I have an upward pulse meet a downward pulse. So if the red pulse starts over here and it's up, and then the blue pulse starts over here and it's down, when they overlap, the red and the blue are going to cancel. And that gives me that green line right there in the middle. Okay. Now, resonance is what happens when an object vibrates at its natural frequency of a second object and causes it to vibrate. So we looked at resonance a little bit when you guys did the Speed of Sound lab. So whenever you were messing with that tube and you pulled the tube back and you found that area where all of a sudden it got louder, right? The reason why it got louder had to do with interference, right? Those waves were overlapping on one another, and you had an antinode at the end there that got really loud for you, right? Or at least loud enough so you could hear it. Due to the cyclical nature of waves, wave interference can result in what's called a standing wave, right? Again, this goes back to your waves in a tube thing, right? So you pulled it back until you found just the right point where that wave was a standing wave. A standing wave appears to not move along its medium, but rather has points of alternating displacement called antinodes and points of no displacement called nodes. How can we have no displacement along a wave? Well, it has to do with destructive interference, right? When the waves cancel out, it doesn't move. So here's nodes and antinodes, right? So all we can see is these are going up and down. This is more of a diagram of a transverse wave, right? But longitudinal waves work the same way. Basically, you have these points, nodes right here. This is a node right here. It's not moving, right? It doesn't go up or down. Over here, I've got another node, right? It's not moving, going up or down. Here, I've got an antinode where I have lots of movement, right? All the way up, all the way down, back and forth. So the collection of different resonant frequencies for an object are called the harmonics. Harmonics are multiples of the fundamental, the lowest standing wave pattern of resonance, or the one that has the least number of nodes. So think about your harmonics for a second. This would be on a string, right? So for standing waves in a string, I need nodes on the ends, right? There exists a fundamental or a first harmonic, right? A fundamental frequency that will make this vibrate back and forth. If I double that frequency, I get 2 antinodes going back and forth forming this wave pattern. If I tripled the fundamental frequency, I would get 3 antinodes, right? You might have not noticed this when you did your labs, but these were multiples of each other, right? The 4th harmonic was 4 times the frequency of the 1st harmonic. The 3rd harmonic was 3 times the frequency of the 1st harmonic, and so on. Okay, we can have standing waves in open-end air columns. So columns that are open on both ends might look like this. On the open end, I need an antinode, right? Antinode on the open end. Now I can add another antinode to it, right? I can add another node, another antinode. So now still, as long as I have the antinodes at the end, this would be the 2nd harmonic, and then the 3rd harmonic, and so on. Okay. Now for your lab, we used a closed end air column. So when a column is closed at one end, but open at the other, it looks like this, right? So we had the 1st harmonic here, right? So this is a quarter of a wave, right? I started at the equilibrium point, and all I did is I made it to a crest. If I'd started at the equilibrium point, gone to a crest, and made it back down to the equilibrium point, that would be a half a wave. If I start here, I go to the crest, I go down, I go to a trough, and then I come back to equilibrium, that's a full wave. Okay, but starting at the equilibrium point and going up to a crest, this is only a quarter of a wave. Now this is the 1st harmonic, right? The next harmonic looks like this. Okay, so again, I need the antinode at one end, right? And then I need a node at the closed end. Now notice this goes from the 1st harmonic to the 3rd harmonic. That's kind of weird. In the open pipes on both ends, or on the waves in the string, we had the 1st, 2nd, 3rd, 4th harmonic, right? This goes 1st, 3rd, 5th. Why does it do that? Well, think about this. This is a quarter of a wave. Look at this one, right? I have a half a wave, and then I have another quarter of a wave. This is 3/4 of a wave. That's 3/4 of a wave right there. So I go 1/4 of a wave, 3/4 of a wave. Well, guess what the next one's going to be? This is half a wave, another half a wave, and then a quarter of a wave. This is 5/4 of a wave. Okay, so because of this limitation that I need an antinode at the open end and a closed node on the other end, I have to add I have to add another half a wave every time to get to the next harmonic. So there's no way for me to have this is a quarter of a wave. There's no way for me to add one more quarter of a wave and still have a standing wave in a tube that's open on one end and closed on the other. So on the closed end air columns, this is kind of the special circumstance. We go 1st harmonic, 3rd harmonic, 5th harmonic. Okay, and that's it. If you have any questions about sound waves, please come see me.